Hello, this is Sandy Pullen for lesson 7.08 on the two-sample t-test. We're going to go over in this video example 1. Patients experience symptoms of heart attack are routinely transported to a hospital in an ambulance. In a study of a new treatment thought to reduce damage to the heart, patients experiencing symptoms of a heart attack were randomly assigned into one of two groups. During transportation to the hospital, patients in one group received standard care. Patients in the second group received a treatment consisting of standard care plus the application of a blood pressure cuff. The response variable measured for each patient was a number between 0 and 1, referred to as the myocardial salvage index, MSI. A higher MSI value indicates a more positive outcome for the patient. Summary statistics for the MSI responses of the two groups are shown below. Does the data provide convincing statistical evidence that the new treatment results in a higher mean MSI value than does the standard care among people similar to patients in the study? So when you look at this problem, the first thing you should think of is, well, they're asking for convincing evidence, so they're looking for some sort of hypothesis test. We also know we have two independent treatment groups, two samples, and the data is quantitative. You're looking at this index, the myocardial salvage index. It's a quantitative variable, and you're comparing these two treatments. So this is when you would use a two-sample t-test. And we go through the four-step process, and the first thing we need to do is define our parameter, state the hypotheses, and state the significance level. Notice that this was a former AP question, and they didn't even give you the significance level. That means you can choose any on your own. So first, we're going to look at, since it's two, the difference of two quantitative variables. And you could either go mu1 minus mu2, but I said mu-n, standing for the new treatment, versus minus mu-s. And you clearly define this in your problem. You can put the video on hold if you need more time to write this down. The next thing you want to do is state the null hypothesis and the alternative hypothesis. Your null hypothesis is always that the two are equal, or that the difference, mu-n minus mu-s in this case, is equal to 0. The alternative, we're expecting a better myocardial salvage index, a higher one for the new treatment group. So it's mu-n minus mu-s is greater than 0. And I chose an alpha of 0.05, but you could have chosen any one in this problem. You now need to verify the conditions. And so the first condition is the patients were randomly assigned into the treatment groups. I just realized I didn't open up my calculator, so I'm going to open it up now and continue on with the rest of the conditions while we wait for it to open. So patients randomly assigned to treatments groups as stated. The second condition, because you have random assignments, you don't really need the 10% condition, but if you're ever unsure, you can add it in. You're not going to lose points. So it's reasonable to assume that they're more than, I combine these two together because you're dealing with the same group of patients. So 56 plus 56 is 112 patients experiencing heart attack symptoms, symptoms of a heart attack. So it makes sense to combine the patients together, since you're pooling from the same group before you randomly assign them to treatment. The next condition, what do you notice? Both our sample sizes are greater than 30, so that means we can apply the CLT. Let me just see how our calculator is doing, because we'll need it in a second. So I'm just opening it up to get it ready. And now we can say for that third condition, since the sample sizes of both groups are greater than 30, we can apply the CLT, the central limit theorem, and approximate the sampling distribution with a normal model. Okay? Now, again, at any point in this video, since I'm going fairly fast, you could put the video on hold so you can transcribe or enter this into your own problems. And the fourth condition, you don't have to write it down, but again, I'm emphasizing it. The population standard deviation is unknown for both groups. That's why we're using a t-distribution, okay? Since conditions have been met, the name of this test is called a two-sample t-test. And we have to write down the degrees of freedom. And I'm going to show you how you get that, because we're not going to plug into the formula. We're going to be pulling that information off of our calculations. Okay, so I'll show you in a few minutes how we get that. So we're going to do the calculations and then we'll go back and fill in the degrees of freedom. So to do the calculations, the general formula is it's a t, not a z, because you're dealing with a t-distribution. It's the statistic, which in this case is the difference of the two sample means, not the population means this time, the sample means. So x bar n minus x bar s minus mu n minus mu s, that's our parameter, over our standard deviation. That's Sn squared over N1 or Nn plus Ns squared for the standard deviation over Ns. And again, you get this information directly from the formula sheet. And notice that the standard deviation is the same one that we use for confidence intervals. We're going to substitute in the information from our problem. Again, I had my new mean, the new treatment mean first. So that would be 0.69 minus the mean for the standard care. That would be 0.57 minus, and the difference of the mean is 0. That's what's defined in our null hypothesis. If you look back in our null hypothesis, we're saying it's 0. So we're assuming that to be true. And this is over the square root of 0.27 squared, that's the standard deviation for the new treatment, over the sample size, plus 0.26 squared over the sample size for the second treatment group. I'm going to make my bell curve, which I should have made in the beginning. We're assuming no difference, and we want to find our p-value, and we're going to calculate our test statistic using the calculator. So the p-value is the probability of getting a difference of the sample means greater than or equal to, well, 0.69 minus 0.57 is 0.12. So how likely, if we assume that there's no difference, do we get a difference of 0.12? That's our p-value, and this is a right-tailed test because we're only looking at the right side. I'm making a video. I can't talk right now. Bye. So This is the probability that T is greater than or equal to, and now we're going to figure this out in the calculator. So I'm going into my calculator, and we're going home. We're going to a calculator page, and we're doing menu, statistics, and whoop, the calculator's very sensitive. Hold on. The online one, statistics, stat test, and it's called a two-sample t-test, as I mentioned before. So two-sample t is right here. And we're going to be inputting summary statistics in this problem and hitting OK. And make sure you're following the same way you substituted in the formula. So I did 0.69, and the standard deviation was 0.27. The sample size was 56. For the second one, it was 0.57, a standard deviation of 0.26, which was slightly less, and a sample size of 56. You have to be careful to scroll down because it was hidden before. We're assuming that the new treatment has a higher success rate than the standard treatment, so it's mu1 minus mu2, and you're not going to pool. The only time you pool is a two proportion z-test, and you hit OK. And notice that you get a t-statistic of 2.3957, a p-value of 0.00914, and a degrees of freedom, and I'm going to round down, of 109. So it gives you all that information. So I'm going to put that in. So again, my t-test was 2.3957. Let me just go back a page. Our degrees of freedom was 109, because you really need to fill that in. Or I rounded up, but I probably would round down. And now we want to calculate our calculations. Now, if you were to do it by hand, because you'll see there are times you need to do it, you would use TCDF as opposed to normal CDF. You would do 2.3957, 9E999 to the end of the right curve. And then you would enter in the degrees of freedom, which I had as 109. That should equal to the p-value of 0.0009. So let's just double check so you can see how this works in case you have to do it by hand, and there are times you do. So you would do menu, statistics, distributions, TCDF. You would enter the T statistic of 2.3957, 9E999, and the degrees of freedom, which we said was 109. And you notice that you get, I got 0.009. Let's see if I wrote it. I wrote it down before, wrong before. It is 0.009. So I'm glad I double checked with the calculator. So I had an extra 0 in here. But essentially you get the same p-value. So you don't really need to do the TCF, but for now I want it. And I'll explain to you when I see you on Monday why it's necessary at this point. In any case, this is a very low p-value, right? Because we're almost up to the conclusion. And we're comparing our alpha of 0.05, which we decided in the very first step. And since it's less than 0.05, we're going to reject RHO, and we do have convincing evidence, but we have to write this up. And this is going to be pretty standard to what we've done in the past. So assuming HO is true, mu n minus mu s is equal to 0, there is a 0.009 probability of getting a difference in sample means of 0.12 or greater purely by chance. And then we say, since conditions have been met, or forget that, that's incorrect. Since the p-value is less than, I'm going to put this back to 0.05, though I could have used 0.01, that would have worked just as well. We reject HO, and we have convincing evidence that this new treatment results in a higher MSI value than the standard treatment among the people similar to the patients in this study. Okay, so you may have to put this video on hold to go back over and make sure you get all this information into the notes. This is a very standard type of problem that you would see not only in AP statistics exam, but in real life. A lot of times we're doing studies where we're comparing two treatments to see the effectiveness of a new procedure or a new technique or a new medication. Have a great day and go on to the second video now.